Welcome to R6 factoring. The process of finding polynomials whose product equals a given polynomial is called factoring. Consider the polynomial 4x plus 12. We can use factoring to represent it in factored form. 4 times the quantity x plus 3, since both 4 and x plus 3 are factors of 4x plus 12. A polynomial that cannot be factored is a prime polynomial. A polynomial is only factored completely when it's written as a product of prime polynomials. So you cannot break anything down any further. Then you know that you've factored completely. Let's take a look. This first section is about factoring out the greatest common factor. So greatest common factor, I have two terms here in this binomial. There's a 9, there's a coefficient of 1, there's 5 y's here and 2 y's here. So the common factor, or the greatest common factor that's found in both of these terms, is y squared. And if I pull a y squared out of the first term, I'd be left with a 9y cubed. And if I pulled a y squared out of the second term, I would just be left with a 1. This is what it looks like to factor out the greatest common factor. A way that you could check, and we're not going to do this for all of them, but you're always welcome to do it, is to then multiply it back like we learned in the previous lesson to see that you get what you originally had. Okay, so I know that I did factor this properly. The green in this case would be my answer. Okay, so here I'm looking, here I have a 6, an 8, and a 12. So the greatest common factor there would be a 2. This, I have 2 x's, 1 x, and no x's. So x is not a part of the greatest common factor because it's not in all. It's not common to all 3 terms. But there's a t, there's a t, there's a t, so I can pull a t out. This would leave me with 3x squared plus 4x minus 6. And lastly, it looks a little complicated, but we're going to simplify it real quickly because what I want you to notice between the 14, 28, and 7, there's a GCF of 7. GCF is a short way for greatest common factor, right? And also, look what's in all 3 terms. M plus 1, the quantity M plus 1, there's 3 of them in the first term, there's 2 of them in the second term, and there's 1 of them in the third term. So I can pull that whole quantity out, 1 of them, and see that I'm left with a 2, and then I still have 2 quantities of the M plus 1. Then let's see, at 28, I pulled out a 7, so I'm left with 4 times M plus 1. And finally, a negative 1. Okay, we're not going to leave it like that. What I want you to notice at this point is, let's change our color. This right here we want to work with. So let's see, 7 M plus 1 is just chilling in the front. Then I'm going to have 2 times, I'm going to write this out to help me see what's going to become of it. I'm also going to distribute this and bring down that negative 1. All right, let's keep going. So 7 M plus 1, 2, it's going to give us an M squared plus 2m plus 1 minus 4m minus 5. And next we can have 7m plus 1. We can, let's see, I'll leave it for now. 2m squared plus 4m plus 2 minus 4m minus 5. Okay, and finally we have made it to the end. 7m plus 1 2m squared, I can, those sum to 0, and that's going to give me a -3. All right, I think we got there. Go ahead and pause and give yours a try. All right, pausing again as you check those 3 answers. Revise as needed. Next, when a polynomial has more than 3 terms, it can sometimes, keyword, be factored using factoring by grouping, okay? You'll want to group the terms so each has a common factor. Did I not put what? Okay, I guess this is example 2. Yeah, I just totally skipped that title there. So this should say like example 2, factoring by grouping. Okay, so here we go. Let's see. Okay, so sometimes this will be like nice and in the right order, and sometimes it won't. So I'm going to show you some issues. So here, if I group these up into these pairs, then I'm looking at this first pair, and I want to pull out the greatest common factor, right? So that each group has a common factor. But there's nothing in common here, just besides the number 1. And then I look over here at this pair, and there's nothing in common here besides the number 1. So this particular way of pairing up these terms is not going to be beneficial to me. I'm going to want to rearrange. So let me try something else. I'm going to take a step back and look at these, and maybe I see to myself, okay, well, the first and third terms both have a 2 in them, and the second and fourth terms both have an A. So let's go with that. Let's write 2y squared minus 2z, because I'm just rearranging how they're written, right? Using our properties, plus az minus ay squared. So now if I pair these up and pair these up, let's see. Here, the GCF, or greatest common factor, I could pull out front would be a 2, and I'd be left with a y squared minus z. And then over here, I could pull out an A, and I'd be left with a z minus y squared. Now here's the issue. This right here is not the same as this, right? So what I would want to do, I could do a couple things. What if instead I let's go with this and close that. What if I kept this like it was, and instead of pulling out a positive A, if I pulled out a negative A, then I would be left with a negative z plus y squared. And now, are these the same? Yes, they're in a different order, but they are the same. So what that means is that these are now a GCF of this polynomial. And so I can write it out front and then write what's left over as the second quantity. That's one way I could have gone about this problem. But notice the orange part, right? They need to match. If they're not matching, then you need to rearrange. You cannot keep proceeding forward. Okay, let's look at the next one. So if we just go with how it's written here, I look at these first 2 terms, there's a GCF of 2x squared. That leaves me with 2x plus 1. Here, I can pull out, let's say we're going to pull out a 1. That's going to leave me with negative 2x minus 1. Now looking here, I'm going to do it in the same color. Are these the same thing? No. So I need to revise, okay? And maybe you already saw it. I purposely wanted you to see this, right? 2x squared, 2x plus 1. Instead of pulling out a 1, let me pull out a negative 1. So that's going to leave me with 2x plus 1. And now I can see that these do match, right? Here they did not match, here they did match, Here they did not match. Here they did match. So I could proceed forward with this. All right. So because this polynomial has a GCF of 2x minus 1, it can be pulled out front, and what remains is 2x squared minus 1. Love it. All right, your turn to try the next two. All right, checking these two. Again, pause as you need to work through them again, as you need to look at things for a little bit more time. And now we're on to example 3, factoring trinomials. Okay, the book just kind of like, assumes you guys are really good at this, and oftentimes we need a lot of practice. So I'm going to kind of slow it down. I'm going to show you the way I do it, but if you have a different way that works for you, by all means do that. So first thing we always want to do is check for GCF, and in this one there is no greatest common factor. So the next thing I do, because there's an a value, we've talked about before, ax squared plus bx plus c, because this leading coefficient or the a value is not 1, I'm going to ask myself what multiplies to give me a times c, or in this case, what multiplies to give me 24, and then what adds to give me b, or in this case, negative 11. So I want to find what multiplies to give me 24 and adds to give me 11. And I come up with the numbers negative 8 and negative 3. If I multiply those together, I get 24, and if I add those together, I get negative 11. So why do I want those? Because they are going to be used in place of that middle term. So let's take a look. We are going to bring down the 4y squared, and we're going to bring down the plus 6. And instead of having minus 11y, I'm going to write it as minus 8y minus 3y. Notice that this is exactly the same thing as what I started with, right? It's equivalent. But by doing this, I've now created a 4-term polynomial that will work with my factor by grouping. So I can break this up into my 2 groups, pull out my GCF, and over here pull out my GCF to get my answer. Oh my gosh, it's amazing how math builds, right? We're using all these skills that we just previously learned. Super. So that is how I go about this type of problem. Okay. So next, same thing. I see no GCF. I see my a value is greater than 1. So I'm going to ask myself what multiplies to give me negative 30 and what adds to give me negative 7. And I come up with the numbers negative 10 and a positive 3. Okay. They're going to multiply to give me negative 30 and add to give me negative 7. So remember, those are going to replace the middle term. Let's just change it up to break things up here. So we're going to have 6p squared minus 10p plus 3p minus 5. We're going to factor by grouping, take out our GCF, and we end up with 3p minus 5 times 2p plus 1. Super duper. Okay, let's go with this color here. Again, no GCF, a is greater than 1. I need to find what multiplies to give me negative 36 and will add to give me 13. So sometimes if I have a larger number or something that's going to have a lot of factors, I like to list them out. So for the beginning, I just don't worry about the signs, and I just say to myself okay, 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't go in, 6 times 6. Those are my list of factors to make 36. And now that I have those, I'm asking myself, could I combine those in any way to get to 13? right? So I might think like, oh, this one looks promising, right? Now let's worry about the signs. If they need to be the same sign, they need to be opposite signs to give me a negative product. So either -4 times 9 or +4 times -9. But notice that either one of those that I have are not going to add up to give me 13. And nothing else on this list works. So what does that tell me? That this polynomial is prime. I did have to go through and check. I didn't know just right away. But if you can't come up with something after a thorough list, then you can, confidently say it's prime. Okay, next one. Ooh, what jumps out at me here? I see even numbers, right? I see y in every term. This is going to have a GCF. So let's do this one. So what is the GCF here? I can pull out an 8y. And now what's it look like? 2y squared plus 3y minus 2. Oh, okay, that's a lot nicer, right? Not as big numbers. Now, I'm just going to focus on this right here. I have a trinomial. There's no more GCF. The a value is greater than 1, so I want to ask myself what multiplies to give me -4 and adds to give me 3. And I'm going to come up with, let's see, I'm going to just let that 8y chill out front. Keep the 2y squared, keep the -2. What am I replacing this middle term with? Multiplies to -4, adds to 3. So I'm going to say a +4y and a -1y. Okay, now I'm going to do my factor by grouping with these right here. So again, that 8y is just chilling out front. Pull out my GCF and write what's left over. Notice how I'm organized and I'm working, vertically, top to bottom. Let's see, 2. Okay, then we're going to want a -1y plus 2. Okay, so the GCF I have going on right here is y plus 2. So I have my 8y, y plus 2, 2y minus 1. All right, looks good. Now it's your turn. Go ahead and pause and try. All right, checking those 4 answers. I did give you a prime one. Did you figure that out? Okay. Example 4, factoring perfect square trinomials. We talked about this in the previous lesson. I recalled for you right here what the pattern looks like, right? And we talked about if there's a plus on top there, that's because there's a plus on top there. If there's a minus there, there's a minus there. And that third term is always going to be positive. Okay, so noticing here, what you would say to yourself is, hey, 16 is a perfect square. P squared is a perfect squared because it's coming from 4p squared. Also, 25q squared comes from 5q quantity squared. So those are going to represent your x and your y. And then checking again right here in the middle, it should be 2 times 4p times 5q. So sure enough, that's going to give us 8 times 5, which is 40pq. So yeah, when I see this, I say this is a perfect square trinomial. And I know that a perfect square trinomial is going to factor into 4p minus 5q quantity squared. Okay. Next one is for you to do. So pause and try. All right, should have gotten 7x plus 2y quantity squared. Another thing we're calling back is the difference of squares. Okay, so I put that here for us to remember. This is again where we have perfect squares that are being subtracted. It will give us x plus y, x minus y. So here I know that this is a perfect square and this is a perfect square. that's being subtracted. So it's going to break down into 2m plus 3 and 2m minus 3. This one a little more complex looking because, bigger numbers, bigger exponents. We know that 256 is coming from 16. K to the fourth, we could say k squared. So notice if I take that quantity and square it, it's giving me this. Then we have another difference or subtraction. And 625 is coming from 25. M squared. I know I skipped over that. We'll have to go back and get that. So I can factor this difference of squares into 16k squared plus 25m squared and 16k squared minus 25m squared. Now, I'm actually not done with this problem because it's not factored completely. Factoring completely means that I can't factor any part of it anymore. But notice what we have going on right here. It's a difference of squares because we got more perfect squares and we got another subtraction. Okay? I guess I should go back up to this note. In the real number system, we cannot factor a sum of squares. Instead, we would say it's prime. So this, notice, is a sum of squares. So this part cannot factor any further. It is prime. That's going to become part of my answer. It cannot break down any further. But this second quantity can. It can break down into a 4k plus 5m and a 4k minus 5m. So just always check at the very end, can I break anything down anymore? All right, your turn. And checking those two answers before we move into sums or difference of cubes. Okay, so this one we did not talk about in the previous lessons. Notice here we can have either a sum or a difference of cubes that can factor, and they're gonna both follow the same pattern. The way I do it is using A's and B's. The book uses X and Y's, obviously same thing. It's just, this is how I feel like it goes better with A's and B's. So what I tell the kids is when you see that you have a sum or difference of perfect cubes, from that problem, you're going to figure out what your A and your B are. And then you're going to say to yourself, A, B, A squared, A, B, B squared. And that's going to be how you're writing out your answer. So let's take a look at this first one. I recognize that this is a perfect cube because it's x to the third power. And 27 is also a perfect cube because it is 3 to the third power. So I have a sum of cubes. That means that my A is x and my B is 3. So when the pattern for my answer says A, B, A squared, A, B, B squared, I'm going to write in x, 3, x squared, 3x, 9. Okay. And then we have this right here, this acronym SOAP, S-O-A-P, like wash your body with soap. And it stands for same, opposite, always, there we go, positive. Using the first letter from each of those words, right? Same, opposite, always, positive. So what that means is in this particular problem, we are adding. So when it says same, we need to put the same sign as our problem. Then it says opposite. If we're adding in our problem, then we need opposite of that. And then finally, always positive. So it does not matter what our problem has, we are always positive there. Okay, so this will be our final answer, okay? These will always be prime, assuming you didn't have a GCF or anything going on that you forgot to pull out. So there would be no need to further factor. Okay, let's look at another one. Go away. So I look at this and I say to myself, well, this was m and it got cubed. And this was 4n and that got cubed. And it's a difference of cubes. So A is going to be m and B is going to be 4n. So when I ask for A, B, A squared, A, B, B squared. And then we can also fill in our signs, right? Because we talked about those. This problem is subtraction. So when it says same, I need to put subtraction. When it says opposite, I need to put addition. And then always positive. So filling this in, we're going to get m minus 4n times m squared plus 4mn plus 16, be careful there, be careful, n squared, right? I need a b squared. You're squaring this whole thing. So the 4 squared and the n squared. So this is our final. All right, let's do one more together. So this is coming from, let's see, we would have had 2 and q squared, all of that cubed. I kind of got to think backwards for a minute, because if I do 2 cubed, I get 8, and q squared cubed, q and q, it's kind of confusing. When we have power raised to a power, we multiply, and so that's where the 6 is coming from. Plus, this is going to be a 5p to the third, all to the third. Okay, so now I have figured out my A and my B. So writing in our answer, remember, until you get better at it, I like to write it out, okay? A, B, A squared, A, B, B squared. And then for our signs, it's SOAP. Same, opposite, always positive. This is an addition problem, so I need the same, then I need the opposite, and then I need always positive. So I need A plus B. A squared is going to be 4q to the 4th minus A times B gives me 10q squared p cubed plus 25, running out of space. Can I move that over? Yes, 25. Let's make that a little better. Plus 25 p to the 5th. No, to the 6th. Oops. There we go. Okay. Goodness. To the 5th, to the 6th. We're squaring. We're squaring. Yeah. Why do I have that? Okay. I think I'm good. All right. Now you get to try the next 3. All right. Checking those. All right, so you're checking those 3. Again, pause as needed, and let's go on. Last part, factoring by substitution. So this is for like more complicated polynomials. Actually, guys, they could have used this method to help them, the AP Pre-Calc kids, on the AP exam last year. So those of you that know you're going to move into that course next year, this is something to think about. So I'm looking at this and I'm kind of like, okay, it's a trinomial, we're good. But then you're like maybe caught off guard because of the like 4th power here. So what you could do is make it into something that you're used to. We're going to use what's called U substitution. So let U be Z squared. So anytime I see a Z squared, I'm going to replace it with a U. What that's going to look like is 6 U, but I need U to the 4th, so I'm going to square this, minus 13 U minus 5. And simply by making that substitution, now it looks like a trinomial that I'm able to work with, okay? So I want to find something that multiplies to negative 30 and adds to negative 13. And so I'm going to use a negative 15 and a positive 2 to replace this. So we're going to have our 6u squared that comes straight down, our negative 5 that comes straight down, and we're going to, what did I say? I said a negative 15 and a positive 2. Okay, now that I've done that, I will factor by grouping like this. So my GCF is going to come out as a 3u, 2u minus 5. The GCF here is just a 1, 2u minus 5. Remember what I said, always make sure that these little guys are matching, right? And because they match, we can pull them out as a GCF and then write what remains. Now, here's the thing to remember, star, star, circle, circle, re-substitute back. Okay, if I can spell. Re-substitute back. So we're not done. That's not where you stop. You need to substitute back in whatever we have. For wherever we have a u, we're going to put a z squared. So we're going to write 2z squared minus 5 times 3z squared plus 1. And then check, can I simplify any of that? Or sorry, can I factor any of that further? No, that's where I'm done. All right, let's do one more together. This one, I would say to myself, well, this quantity is being cubed and this is 2 cubed. So this makes me think of a sum of cubes. But it just looks a little bit complicated because of that first part of it, the first term. So let's say, let u be 2a minus 1. Now what is it going to look like? It's just going to be u cubed plus 8. Well, that's simple. I've worked with that before. Okay, remember, this is coming from u to the third power plus 2 to the third power. So these represent my a and my b. And if we need a refresher, the pattern is a, b, a squared, a, b, b squared. And then we use SOAP for our, the operations. Same, opposite, always positive. So in this problem, we have a plus. Same, opposite, always positive. Now let's actually fill in using our a and our b. So we're going to say u plus 2 times u squared minus 2u plus 4. You're not done. You have to re-substitute back, right? Re-substitute. So let's change our color. And instead of a u, we're going to have 2a minus 1 plus 2 and 2a minus 1 minus 2 times 2a. Ooh, this is getting, this is thick. I am in the middle of it. Okay, let's see. We can combine like terms here to get 2a plus 1. Over here, see, I'm more visual. I gotta write it out sometimes, especially if I'm supposed to be talking while I'm doing it. So that'll be simple enough. Let's do that, that, and that. Okay. Whoops, go away. Boop. Okay. And let's keep going. 2a plus 1. You're just hanging out in front. This is going to give me what? 4a squared minus 2 minus another 2 plus 1. And this should be our last line. Let's see here. 2a plus 1, 4a squared minus 8a plus 7. If I did that right, I think we're good to go. All right, your turn to try the last two. All right, and checking those two, and I will see you in class. Bring those questions with you guys. Thank you.